and welcome back to your distance learning lessons. Today we are going to be looking at the 3 gas laws that are really important for our topic on thermal physics. So since we've already started this topic today, we're going to start with a knowledge retrieval. I'd like you to take 2 minutes and look at the following slide, pause the video and then work your way through those 4 questions. Okay, so by now you hopefully will have paused the video and worked through those 4 questions. Let's have a look at the answers to these questions. Question number 1 asked you, what is the lowest possible temperature that an object can theoretically reach called? That is absolute 0. It's the same as having minus 273 degrees C or 0 Kelvin. Question 2 asked what is meant by the internal energy of a body. Internal energy of a body is the sum of the randomly distributed kinetic and potential energies of a particle. Question 3 asked for the definition of the specific latent heat of vaporization. That is the quantity of thermal energy needed to be transferred to boil or condense 1 kilogram of a substance. And question number 4 asked, what effect does increasing the temperature of a gas have on the speed of the gas molecules? Well, if we increase the temperature, then the average speed increases. That means that the average kinetic energy will also increase, and therefore the distribution of the molecule speed becomes more spread out. So that's thinking about that graph that we learned in the lesson on Monday, and that we saw that we'd have a kind of squashed curve for higher temperatures. We're going to be concerning ourselves mainly with an ideal gas. An ideal gas essentially follows the 3 gas laws that we're going to be looking at today. It will describe how a fixed mass of gas behaves if we change the temperature, the pressure, or the volume. The one main assumption that we have to make here, apart from the fact that we're looking at ideal gases, is that all of our temperatures are measured in the Kelvin scale. So if you see anything at any point that is measured in degrees C, it is absolutely essential that you change that to Kelvin for these laws. So, Boyle's law is what comes first. Boyle's law states, and you do need to know these definitions and these laws off by heart in case you're asked to define them in your exams, that at a constant temperature, the pressure, P, and the volume, V, of a gas are inversely proportional. In other words, as we increase the pressure, we decrease the volume, or P is inversely proportional to V. So that's what we need to be thinking about. So if we reduce the volume of a gas, then the particles end up becoming closer together. They'll collide with each other and the side of the container much more, and therefore the pressure will increase. Our ideal gas will obey Boyle's law at all temperatures. Therefore, we could also say that Boyle's law means that at any given temperature, the product of P and V will always be the same, i.e. it's going to equal a constant. Therefore, P multiplied by V is going to be equal to some constant. And you'll see several graph representations of Boyle's law as well. So if we think about it, if we've got our pressure on our y-axis against our volume on the x-axis, then for different temperatures, we're going to see our inversely proportional relationship between pressure and volume. So this is our first temperature, let's call that T1. If we have a different and separate temperature that we can call T2, we'd expect something like that. And then finally we had something T3. We would expect something like that. Not only obeys Boyle's law, but it also must obey a second law that we call Charles's law. Charles's law states that at a constant pressure, the volume, V, of a gas is directly proportional to its absolute temperature, T, and remember that temperature is in Kelvin. So, if V and T are directly proportional, we can obviously say that this relationship will hold. At the lowest theoretically possible temperature, which you've already told me in your knowledge retrieval is absolute zero or 0 Kelvin, then if Charles's law is obeyed, the volume divided by the temperature is going to give us a constant. In other words, V over T is equal to our constant. Again, we can represent this on a graph. For example, at absolute zero, if we could take readings at that temperature, we would expect to see our graph look something like this. So there's our volume, there's our temperature, there's absolute zero. We'd expect that. Most of the time, however, we can't replicate those conditions in school labs or even in some actual quite good labs. So a lot of the time, if you're doing this experiment, we would end up having a graph that looks something like the following. Where our line would cut the axes somewhere like that, and we would have our theoretical temperature of absolute zero written there. So obviously when you heat a gas, particles will gain kinetic energy. We've seen that already when we've looked at our knowledge retrieval and last lesson, and therefore they'll move more quickly. At constant pressure, that means that they move further apart, so the volume of the gas is going to increase. The final law that our ideal gas needs to obey is something called the pressure law. The pressure law states that at a constant volume, the pressure P of an ideal gas is directly proportional to its absolute temperature T, which again is measured on our Kelvin scale. So for example, if you heat a gas, the particles will end up gaining kinetic energy. That means that they move faster. If the volume does not change, then the particles will collide with each other and their container more often, and at the higher speeds that will increase the pressure inside of the container. At absolute zero, the pressure of a gas must also be zero because we have no movement, therefore no collisions. If the pressure law is obeyed, that means that we have a pressure divided by temperature is equal to a constant. So once again, we see our relationship something like the following. Therefore, P over T is equal to a constant. And we end up with very similar graphical representation to Charles's law, whereby for a gas at absolute zero, we can draw our pressure temperature graph. And it looks something like that. Most of the time, however, as you obviously know, if we're measuring in a Celsius scale, which we most often do in the lab, we'll end up with something like that, where once again that is our minus 273.15. Okay, that essentially brings us to the end of the 3 important gas laws. We'll be using those next week to look at something called the ideal gas law. What you need to do now, though, is that normally this lesson we would be doing our first year 13 required practical for verifying the gas laws. Now you would do that to look at both Boyle's law and Charles's law. So if you read the sheet that I've provided with you that has the instructions for today's lesson on, part of that will be for you to go away and investigate the 2 experiments that we could have possibly carried out in order to complete our required practical. Have a look at the videos that I've attached to your instructions. Make notes on what the teachers are doing as they go through those 2 practicals, and then write a small method that demonstrates exactly what they are doing to verify both Boyle and Charles's law. On top of that, what I'd like you to think about, because it will be important, and when we do return to school we will be doing this as an actual required practical, are the errors that would come up in this practical instance. So I would like you to think about what kind of errors are present during these 2 experiments and how we could minimise them if you were going to do this experiment yourself. And then hopefully when we come back to school and you do this experiment, you've already thought about the errors and what problems you might be presented with, and you've not done them so that you get the best results possible for your actual required practical write-up. Okay, take care. I will speak to you on Friday unless you don't have any questions about this week's work, in which case I'll see you for our next lesson next Monday.